Today we're diving into something called PMD Based Reactomics. I know, it sounds complicated, but stick with me. It's a totally new way of looking at biology that helps scientists solve mysteries that have been hiding in plain sight, right inside our own bodies. Let's get into it. So I want you to imagine something. Think about trying to solve a crime. You could spend all your time trying to identify every single object in the room, or you could look for the actions, the footprints of forced lock, the clues that show what actually happened. That's the big idea we're digging into. What if the most important clues in biology aren't the molecules themselves, but the chemical reactions that connect them?
And this idea, this shift from looking at things to looking at actions, it leads us right to a massive challenge that scientists have been wrestling with for years. I like to call it the molecular mystery.
Here's the deal. When scientists analyze a sample, like your blood or urine, they use this incredible machine called a mass spectrometer. It's amazing. It can detect thousands and thousands of different molecules. But here's the problem. We can't identify most of them. They're just unknown signals. It's like trying to navigate a city in a super dense fog. You know stuff is there, but you have no idea what it is. And that really holds back our understanding.
So the old school way of doing things was to try and clear that fog one little bit at a time. The process was always detect a molecule, try to figure out what it is, and only then try to see how it fits in with everything else. But that is a huge, huge bottleneck. I mean, identifying every single unknown molecule is often just straight up impossible. They're not in any database, we have nothing to compare them to.
Which brings us to the big question, right? If we can't identify everything, how on earth do we make sense of all this molecular noise? How do we find the really important signals that are buried deep inside that fog? Well, to answer that, some clever scientists decided to just stop looking through the fog. Instead, they started searching for a completely different kind of clue, something called a paired mass distance, or PMD for short. Okay, so this is the crucial part. A paired mass distance, or PMD, is just the exact difference in mass between two molecules. Now, why does that matter? Well, because every single chemical reaction, like say adding a sugar molecule or chopping off a hydrogen atom, that action has a very precise and predictable change in mass. So the PMD acts like a unique footprint, a signature that tells you a specific action just took place. And this right here, this is the paradigm shift. The old way was all about identifying the things, the compounds, and then maybe finding the relationships. The new way completely flips that on its head. It finds the relationships, the reaction footprints, first. We can literally see that a reaction is happening even if we have no clue what the two molecules involved actually are. We're looking at the action, not just the actors. And this incredibly powerful new strategy, this new way of studying the entire universe of reactions happening inside a sample, it has a name. It's called PMD Based Reactomics. Okay, so the concept is pretty cool, right? But how does it actually work in practice? Let's break it down step by step.
It's really a beautiful three-step process. First, the machine does its thing and detects all the molecular signals in a sample. Second, a computer just crunches the numbers. It calculates the mass difference between every possible pair of those signals, creating this giant list of PMDs. And then, step 3, this is the magic, it checks that huge list against databases of known chemical reactions. So, if it finds a PMD of, say, 2.016, the database goes, hey, I know that one. That's the footprint of adding 2 hydrogen atoms.
Now for the really fun part. Theory is great, but let's see how this actually works in the real world. We're going to look at 3 different cases where Reactomics solved a problem that was basically impossible before. Okay, our first case, I'm calling it the polluted pumpkin. It's all about a pumpkin plant that was exposed to a pretty common flame retardant, a pollutant called TBBPA. Scientists really wanted to know how the plant was breaking this chemical down, and the results were just stunning. A previous study had only managed to find 7 of the breakdown products, these things called metabolites, but by using PMD analysis to look for the footprints of the plant's detoxification reactions, the researchers found 15 additional metabolites. That's a total of 22. They uncovered this whole detoxification network that was way, way more complex than anybody ever thought. All right, on to our second case. This one tackles a really basic question. When we find some unknown molecule in our body, how do we know if it's something our body made, that's called endogenous, or if it's a foreign invader from our food or the environment, which is called exogenous? Reactomics gives us this brilliant clue. Think of it like this.
Molecules made by our body are part of this huge interconnected metabolic subway system. They're involved in all sorts of reactions, so they create these really complex, highly connected PMD networks. But foreign compounds? They're kind of like tourists. They might undergo one or two simple reactions, but they don't really plug into the whole system. Their reaction networks are really simple and sparse. And the data just makes this crystal clear. When they analyzed thousands of compounds, they found that, on average, a molecule made by the body is connected to about 4.5 other molecules through reactions. A foreign one, just 1.7. That big difference lets scientists make a really good guess about where a totally unknown molecule came from. So for our final case, we're looking at one of the holy grails of medicine, finding biomarkers for disease. Can reactomics actually help us spot the signature of something like cancer? Well, the answer seems to be a resounding yes. In one study, they looked at urine from lung cancer patients and from healthy people. But they didn't just look for a single biomarker molecule. They looked for a biomarker reaction. And they found one. A reaction with a PMD of about 2.02, which is that add two hydrogens reaction again, was way less active in the cancer patients. That is a completely new kind of clue that all the traditional methods had totally missed.
So let's zoom out. What does all of this add up to? What's the bigger picture here?
This quote from the researchers who came up with this whole idea, it just says it all. PMD Based Reactomics fundamentally changes what a mass spectrometer is. It's not just a compound detector anymore. It's now a reaction detector. We're seeing biology in a whole new way. So, what are the key things to remember? First, Reactomics basically gives our scientific instruments a superpower. They can now see actions, not just things. Second, it lets us pull out these incredible biological insights from that fog of unknown molecules we talked about. And finally, this opens up so many new doors for everything from discovering new disease biomarkers to tracking pollutants in the environment. We started off talking about that molecular fog that was hiding so many of biology's secrets. PMD-based reactomics has given us this incredible new lens to see through that fog and to map out the web of actions happening underneath. So it really just leaves us with this one huge, exciting question. Now that we can see the reactions hiding in the fog, what other mysteries are we about to solve?